Welcome to this video on the periodic table, which is suitable for an introduction really to the periodic table and could be used as a starter point for IGCSE chemistry. So hopefully you have your periodic table in front of you. If you don't, here is a periodic table. Wow, what a phenomenal construction this periodic table is. And you need to know about how the elements are ordered. So why we move from hydrogen to helium, and then on from lithium to beryllium to boron to carbon to nitrogen, etc., etc. And you may think that the elements are ordered in increasing mass number. There are two numbers on your periodic table. There's an integer, a whole number, and that's the atomic number. And then there's a number which might be a fraction or a decimal, and that's the mass number. So maybe I might write that there. So atomic number, and that's the mass number. And the smaller of the two numbers is always the atomic number. Sometimes the atomic number is on the top, sometimes it's on the bottom. But the smaller of the two is always the atomic number. And you should know that the atomic number is the number of protons in an atom. The mass number, well, you could discuss whether it's the mass number or the relative atomic mass. If it's always a whole number, you've got the mass number. If it's a decimal, you're probably dealing with relative atomic mass. And the mass number is the number of protons plus the number of neutrons in an atom. And the relative atomic mass is very similar to that, but it's the average mass of an atom of that element, taking into account the relative abundance of the isotopes. Now I'm digressing a little bit. But the periodic table is ordered in terms of increasing atomic number. So in other words, as you go from hydrogen to helium to lithium to beryllium to boron to carbon to nitrogen, etc., as you move on one element, the atoms gain an extra proton. They increase their atomic number by 1. We go 1, 2, 3, 4, 5, 6, etc. Okay, so you need to know that. It's increasing atomic number. And you should know that the elements can be divided into two subcategories, the metals and the non-metals. And the metals tend to live on the left-hand side of the table, the non-metals on the right. And you should really know where the dividing line between the two of them is, and it's round about here, and it's this staircase that comes down there like that. And the elements on the right-hand side of this, whilst they are non-metals, they're called metalloids. You don't need to know that. But these are all the metals, and these are the non-metals. So metals to the left, non-metals to the right-hand side of that staircase. And I always remember that the staircase goes in between boron and aluminium. So when we talk about the periodic table, we talk about the periodic table in terms of groups and in terms of periods. Now the group number, which are these numbers along here, are incredibly useful for telling us about the elements in the groups. Now the groups are columns, so going down like so, and the group number tells us the number of electrons, and I'm going to abbreviate electrons to E-, the number of electrons in the atom's outer shell. And that's very useful, because what that tells us is that all the elements in, say, let's find group 7. Where's group 7? Group 7 is over here. So all the elements in group 7 have 7 electrons in their outer shell. And that means they all react in a similar fashion. They'll all do similar things, not identical things, they all react slightly differently, but they react in a similar fashion. Likewise, group 1. Here's group 1. Okay, now hydrogen doesn't really belong in group 1, but sometimes it ends up here in the table, sometimes it ends up in the middle. But the metals within group 1, lithium, sodium, potassium, rubidium, etc., all react in a similar fashion. And you're going to look at that in a later video. The periods are the rows. So there's period 1, here's period 2, period 3, etc. And the periods tell you the total number of electron shells that that atom will have. So periods equal the number of electron shells an atom has. So all the elements in period 3 have 3 shells of electrons. So if we pick a random point, let's say here, aluminium is in period 3, so it's got 3 electron shells, and it's in group 3, so we know that of those 3 shells, the outer shell only has 3 electrons in it. Phosphorus is also in period 3. So it has 3 electron shells, but in its outer shell there are 5 electrons. And it's really important you don't confuse the two. We talk about these a huge amount, and the table is incredibly useful because of this instant information it gives us. Now this is a simplified version of the table. We've got group 1 here, we've got group 2, and we've removed the middle block of the periodic table. What we call the transition metals, or the transition elements, we've removed. So we skip all the way to the other side of the block, and here's group 3, group 4, group 5, group 6, group 7, and this final group is either called group 0 or called group 8. So we're now going to write out the electronic configurations for these elements, and you'll see how the trends in the table exist. Now hydrogen has an atomic number of 1, and you can see that from your periodic table, which means it has 1 electron, and that's going to sit in the inner shell. Helium has 2 electrons, and that inner shell can only hold 2 electrons, so that shell is now full. Now you might think, hang on a minute, how can it be in group 8 when it's got 2 electrons in its outer shell? And what I'd say to you is, well, actually the inner shell is a bit of an anomaly because it can only hold 2 electrons, and really what I'd urge you to use is group 0, because that's sort of looking at the shell beyond that 2. Okay, so it tells us that the shell is full. Let's look at lithium. Well, lithium's 1 jump from helium in the table, so rather than putting 3 electrons in the inner shell, they just can't fit. We put 2 electrons in the first shell and then 1 in the next shell. Beryllium has 1 more electron, boron 1 more electron, carbon 1 more electron, nitrogen 1 more electron, oxygen, fluorine, neon. And at which stage you'll hopefully realise that this shell is now full, so we have to start a new shell for sodium. So rather than me talking through all of them, I just skipped ahead a little bit there. But what you can see now is that everything in group 1, even hydrogen, which doesn't always sit here, has 1 electron in its outer shell. everything in group 2 has 2 electrons in the outer shell. 3 electrons, 4 electrons, 5 electrons, and you need to be able to do the first 20 elements, writing out the electronic configurations. And we haven't written the period numbers on here, but you can see that this first row, there's only 1 electron shell. This second row, the second period, there's 2 electron shells. The third row, the third period, there's 3 electron shells, etc. So it's very nice for us to see that the period number works out just as comfortably as the group number. Now, we often refer to groups by names, and it's important that you know where you're going with this, really. So the noble gases is a name that we give to group 0. So all these things down here, that was rather scruffily done, that wasn't very neat, so let's just neaten that up a little bit. All the things in group 0 are known as the noble gases. Now they're called the noble gases because they are very, very unreactive. And the reason they're unreactive is because they have a full outer shell of electrons. They have no desire to lose electrons, they have no desire to gain electrons. Their outer shell is full, so they are very unwilling to interact with any other atoms, which makes them unreactive. I used to go through at school thinking that they didn't react, and it was only when I left school, or it was actually, sorry, no, it wasn't when I left school, it was in the 6th form when I realised that xenon actually does react, and that was a reaction that was discovered in the 60s, and xenon reacts with fluorine to produce xenon tetrafluoride and other fluoride molecules. But it will only react when you put it with something else that is phenomenally reactive, and fluorine is phenomenally reactive. But it is certainly fair to say that they are unreactive, they are very unwilling to react. Helium, you should know, is used in balloons and airships, and it's used in balloons and airships, number one reason, because it is less dense than air, so the balloons rise, and it's a much better gas to use than hydrogen, which also has a very low density, because of its unreactive nature. Neon is used in lights, and again is wonderful because it gives a nice coloured glow, but it is also unreactive, so it prevents any of the things inside the bulb reacting with anything else. We should also refer to group 1 metals, although I know there's another video on these. They're often known as the alkali metals, not because the metals themselves are alkali, but because they form alkalis in water. So they start down here with lithium. And this block in the middle, which you're not really often asked about at IGCSE, are the transition metals. And we study their chemistry at A level. So that concludes this video on an introduction to the periodic table. I hope it's proved useful.